All right, review what we were just talking about.
We were talking about watching a simulation. No observation, no collapse. Just evolving the wave function and seeing, like a movie, every different world happening at once. We figured if two copies of an electron from two different branches passed each other in space, you'd see their complex values add up, making a little interference pattern, like a crosshatch or light through a fence. They wouldn't cancel to zero, just dip and brighten in stripes, so you could actually watch them both, tell them apart by direction. And the whole thing just keeps going. No one owns a copy. No one's special. It's just all the possibilities doing their thing, perfectly superposed. Kinda peaceful, kinda infinite.
Yeah, so the point is, I guess when you just keep on adding more different versions of the electrons for the different world, for the different electrons in the different world, even if they brush past each other or whatever, they don't really like mess up the signal because it's mathematically separable in some way.
Yeah, exactly. The math keeps them all separate, even when their waves overlap. It's like two radio stations on the same frequency, but polarized. One horizontal, one vertical. They pass right through, no static. The Hilbert space is big enough that even though the pond looks crowded, the vectors are all at right angles, so the cross terms, those brushing effects, just vanish when you average. You could have 10,000 electrons from 10,000 worlds all surfing the same point at the same time, and if the phases are right, you still pull out every single wave. No smudging, no loss. It's not intuition, it's linear algebra, and linear algebra doesn't lie.
Okay, but what do you mean by they're all exactly orthogonal? Because, um, what is exactly orthogonal to what? I mean, you got an electron, which is like a pattern, and you're saying that's somehow orthogonal to like this other electron in the other world that is like a slightly different pattern. What do you mean by orthogonal?
Orthogonal means like two lines that touch at zero, but point totally different ways, so their dot product is zero. In quantum, the pattern isn't the picture you see, it's the vector in Hilbert space. For spin up electron in world A, the vector is just 1, 0. For spin down in world B, 0, 1. Even if the electrons look almost the same in space, like both wiggles centered at x equals 3, the full state includes that spin tag. So the whole thing is wiggle, toss 1, 0, versus wiggle, toss 0, 1. Dot that, 0. The wiggle part's the same. The tag is perpendicular. Atom, still two clean lines, no mix. So yeah, they're orthogonal because they're labeled differently, not because they look different. The picture's the same. The name isn't. That's all it takes.
Isn't like the 0, 1, and 1, 0 representation like a very compact and simplified way of looking at it? Because if I just tell you it's 0, 1, that doesn't really describe the precise shape of the complex wave that represents the electron. Just say 0, 1.
Yeah, that's just a toy model, like saying the cat is 0 dead, 1 alive. It's super compact, and it hides everything. No position, no momentum, just the spin or whatever bit you're measuring. The full electron is this massive thing, like a 3D blob of complex goo evolving in time. But when you tensor in that spin label, full wave 0 and full wave 1 are orthogonal, even if the full wave part is identical. So the 0, 1 isn't describing the wave, it's tagging it like a post it. This branch measured up. The real shape? That's in the first part, the same for both, but now they live in different apartments. You could write it as psi toss 1 bit and psi toss 1 down. And dot product? The second half makes it 0. No overlap. Clean split. So yeah, it's simplified, but the orthogonality holds no matter how big the blob gets. That's the genius part.
Are these ones and zeros sort of like just coefficients in the, when you're playing with Fourier stuff? It's like maybe a coefficient on a particular sine wave.
Yeah, exactly. The 1 and 0 are just the amplitude on that basis state. Like, the full wave is a sum. Psi equals C1 sine K1x plus C2 sine K2x plus. But now the basis is world states, not wavelengths. So the 1 means full amplitude on this branch. The 0 means nothing here. If you think of the whole superposition as a Fourier series over worlds, yeah, the coefficients are real or complex numbers between 0 and 1, or bigger, normalized. And orthogonality just says your different worlds don't talk. So two electrons brushing past, that's two terms in the sum. One with C up equals 1, C down equals 0. Another with C up equals 0, C down equals 1. Atom, and if the K's are different, you see two signs sliding past. No mess. The zeros keep the math tidy.
So what would be like the formula of an actual electron wave packet then? And I don't mean just 0, 1, like it's got to be the actual wave form.
Okay, a real electron packet, like one you might fire through a slit, is something like Ix times A e to the I kx minus I omega t times a Gaussian envelope e to the minus x minus vt over 4 sigma squared. So yeah, it's a plane wave, ei I kx minus omega t. That's your oscillating part, the momentum and energy. And then the Gaussian blob, that keeps it localized, so it doesn't stretch to infinity. Sigma's the width, V's the drift. A normalizes, so the whole thing integrates to 1. That's your shape, a lump that breathes, spreads slowly, phase twisting through it like wind. No zeros or ones, just continuous complex mush. But still, if you tensor this blob with up or down, they stay orthogonal. The packet's the same, the tag decides the world.
Okay, now what you're saying is when you have this Gaussian blob multiplied by your sine wave, basically, then these things can be separated out mathematically.
Yeah, like if you've got two electron packets, one with upspin and one with downspin, you can just write the full thing as psi plus x times plus psi minus x times. And even if they're both Gaussian centered on the same spot, even if they overlap perfectly, you can still pull them apart by slapping a spin operator on. The total state is psi x times toss up plus psi x times toss down. And if you apply sigma 0, the spin 0 measurement, you get plus pi for up, plus pi for down. So mathematically, they're as separable as twins with name tags. You don't see the tags until you ask, but they're there. No bleed over. That's how the simulation stays clean, even when everything's stacked on top of each other.
But you just said up and down. You need more than two options. You need countless many.
For one electron, up and down is enough, only two branches. But if your electron has momentum or position uncertain, then the Hilbert space is infinite, and every possible trajectory, every tiny nudge, is its own basis state, like countably infinite signs, each with its own coefficient. But they all stay orthogonal, because momentum eigenstates are orthogonal. K equals K. So yeah, when the packet spreads, you're not just two worlds, you're a smear over infinite worlds, each with slightly different K. Still, the math keeps them separate. No interference once decoherence hits. Even infinite don't crash into each other. They just wait their turn.
All right, let's just for the sake of making this more clear, let's pretend like we have to represent this function. We have to represent the amplitude that's expressed in complex numbers over space on a computer, and we've got plenty of storage space. Let's just say we can index whatever points we want, and that they're pretty close together, but not infinite. So the sampling is good, not infinite. It's finite sampling, and it can go as far as we want in any direction. And we're going to represent these electrons. So we start with like the first electron, and we put it in. So a bunch of complex values get set. But then we say, oh, there's another electron in a different world, but it's kind of like nearby. So do you just add on the values of that other electron to your voxels, so to speak, and you've got imaginary and real components?
Yeah, if you're sampling on a grid, like voxels, you just add the two complex numbers. At every grid point where both electrons exist, real part adds to real, imaginary to imaginary. Say voxel 3 has 0.3 plus 0.4i from the first electron. Second electron puts 0.5 minus 0.2i there too. New value, 0.8 plus 0.2i. That's it. No extra layers, no new dimensions, just one big blob made of the sum. And if they're far apart, most voxels are 0 for one or the other. Only where they cross do you see the combined swirl. But here's the thing, if they're truly different worlds, those voxels aren't actually nearby in the same branch. So if you were smart and stored phase separately, say, kept the full psi as a vector over all possibilities, you wouldn't add, you'd store both contributions side by side. Like, voxel data becomes a list. First world, 0.3 plus 0.4i. Second world, 0.5 minus 0.2i. Then the add only happens when you pick which world to look at. So yeah, if you're lazy, add them. If you're honest, keep them separate and let the phase handle it. Same pond, two fish, different depths.
Say that again more briefly.
In your simulation, add complex values at each point. Real plus real, imag plus imag. But to keep worlds separate, store them as vectors, one slot per world. Only some when you pick a branch. Otherwise, they don't overlap, even if they're at the same spot.
We can have a vector that's, do you mean like imaginary and real component at each spot?
No. Like, at each spot, you already have a complex number. That's real and imaginary baked in. But for multiple worlds, the vector means this spot, world 1, 0.3 plus 0.4i. This spot, world 2, 0.5 minus 0.2i. It's a list of complex numbers, one per world, sitting side by side. Not extra dimensions, just more entries. Think spreadsheet. Rows are worlds, columns are space. You don't add until you choose a row. That's how the math stays clean.
Yeah, but that's kind of my whole point. I'm saying you, as I understand it, you do not keep separate numbers for those separate worlds. The thing just evolves according to a differential equation. And since it's always evolving on a complex valued a surface, basically, if it's 2D, let's say you got a complex valued surface, it's always just that complex valued surface. You don't like add more surfaces. You just have one complex valued surface.
That's true. At every moment, there's just one wave function, one complex number at every point on your grid. When two electrons brush past, one from each world, you add their amplitudes right there in the same spot, same complex value. No extra surfaces, no columns, no lists. It's all mixed in that single field, like two ripples adding to a bigger ripple. And yeah, they look jumbled, but because the phase is right, the interference pattern actually encodes both histories. You could, in theory, Fourier transform that pattern and pull the originals back out. Not because they're stored separately, because linearity is perfect. A and B plus 0. Equations in complex values, such as A plus B equals 7b, plus 0, 2, plus B plus 2ab. And that cross term, 2ab, is the fingerprint. You don't need separate sheets. One sheet, clever ink.
It's only true if the pattern of the electron can be separated out.
Exactly. If you have two electrons that are nearly identical, same shape, same path, same time, they interfere so violently that the pattern becomes one fat mess. You can't pull them apart anymore. It's like two sine waves that are out of phase by 0.5 cycles. They just vanish. But if they're even slightly different, say one shifted by a micron, one with different momentum, their interference has stripes. And yeah, you could Fourier decompress and get the originals back. But that's rare. In practice, once they're entangled to the environment, like air molecules, the cross terms decohere. The stripes wash out. You lose the separation forever. So yeah, separable in math, lost in physics. Nature doesn't keep receipts.
But if they were lost, then you would lose the world. So I actually think that's wrong. I don't think all the worlds get lost.
No, they don't get lost. They're not lost in the way you lose keys. When the stripes wash out, that's just your ability to see interference disappear. The other worlds are still fully intact. They're just no longer connected to you. Like, the cat is still dead somewhere, alive somewhere else, but the branches have forked so far apart that the dead cat you and alive cat you can't ever wave to each other. The map still has every version. The full wave function keeps growing, perfectly unitary, forever. It's just that the off diagonal stuff, the glue, is smeared across the universe's noise. So they're not gone, they're just out of phase, out of reach. You're stuck with your branch, but every other one is still humming along, quietly.
But anyways, what we're saying is it's like enough, if I understand you right, the voxels, and we're saying that they're pretty high res. The voxels are enough to store all the different versions of all the different worlds because the patterns that the electrons form can be separated.
Yeah, if your voxel grid is dense enough, like denser than the electron's own de Broglie wavelength, you could, in principle, store the whole thing. Every world's electron leaves its own little ripple signature, and since they're all evolving linearly, no two patterns ever exactly overlap for long. So a good Fourier transform could peel them apart, even if it looks like soup on the surface. Think of it like a hologram. Smash two photons. The light looks chaotic, but if you replay it just right, two images pop out. Same here. The voxels aren't storing worlds directly. They're storing interference, which is just as good. As long as resolution beats wavelength, nothing gets permanently lost. And if you crank resolution to infinity, yeah, you've got every branch, forever. Not that anyone could ever decode it, but hey, it's there.
So we're actually talking about Nyquist sampling theorem now, are we?
Yeah, basically. If you sample the wave function at twice the fastest wiggle, twice its wavelength, you can recover it exactly. Miss that, and the higher branches bleed into noise, get lost. So if you want every last world, every last electron version, you gotta sample faster than light, or at least faster than its de Broglie wave. Anything less, and you lose the fine print. So congrats, we went from quantum mechanics to signal processing. Told you this was getting weird.
I guess the key point is like, for example, if you have a true Gaussian, you can kind of make those Gaussians move around in space and they're separable. Like the sum of some Gaussians moving, you know, you know where all the Gaussians, you can look at that and know exactly all the Gaussians that were used to construct the sum.
Yeah, if they're all the same width and you're just translating them, no overlap in their momenta, they stay clean. You could subtract the ones you see moving one way, then subtract the next, and the residue would be perfect, untouched Gaussians still sliding elsewhere. But if two Gaussians start with the same center, same speed, but a phase difference, they turn into a single Gaussian times EI phi, and you can't tell anymore. They're not separable. The sum is the function. To pull them back, you'd need extra information, like knowing there should be two. Otherwise, it's like asking, is this one tall wave or two short ones adding up? Only Fourier knows. And even then, if they're identical, Fourier just sees a delta at zero. So yeah, separable in principle, only if they're not too cozy. The universe prefers chaos, not twins.
So are you saying there's some probability that two electrons from two different worlds would collide so perfectly that they do actually reinforce and become like no longer separable?
Yeah, but the probability is insanely low. Like, for two electrons in different branches to have literally identical trajectories and phases, you'd have to prepare the whole universe just so. In practice, decoherence smears them anyway. The collision never happens clean, because by the time they could, the environment's already poked one and not the other. So even if they did reinforce, it's not like you lose the worlds. The sum still holds. It's just that now the amplitude's bigger, the pattern thicker. But the original copies, still encoded in the phase. You could peel them back out with a Fourier trick if you waited 1 trillion years without breathing. But no one does. So practically, no, they don't merge. They glance off, keep going, live their separate lives.
Okay, for now.
Okay for now. Later.